Hi and good day. This is the lecture 7 of the course Agricultural and Biosystems Structures Engineering. The previous topic was on the roofing system, and this time the discussion would be on combined loads or combined loadings. Now, in a certain structural component, okay, the load actually would be resulting from a lot of well, the stresses would be resulting from a lot of loads from various combinations of these loads. That is why it is very much important to take into consideration combined loadings or the effect of the different combined loads in a certain structural component. Now, this will be proceeding or progressing towards the discussion of the transformation of stresses, because in a material, despite their combined, okay, or despite their homogeneity, okay, as seen from the naked eye, a material of a structure would have different, well, in the microscopic level, okay, would have different or would be heterogeneous. Now, this is the case for materials of engineering, where the material components are looked into, okay, at the microscopic level. In the combined loadings, when we go towards transformations of these stresses, the idea is to find, okay, the maximum stresses within a body, so that considering differences in their structural, okay, or yeah, the inner structural components, there is a good, okay, a good insight into how the material will behave and be loaded or stressed, okay, and the corresponding strain or deformations. Now, again, in combined loadings, various loads are are subjected to the component of a structure at any given time. And in this situation, or in this discussion, the discussion will be on the biaxial loading and combined axial and lateral loading. Now, for example, this farm sign, okay, that is shown in figure 1, this sign is subjected to wind load. Okay, let's imagine a wind, okay, going towards this direction. Okay, so there's a wind with a speed v. Okay, so let's read the example first. Okay, we have a farm sign. The dimensions b in height and a in width, that is supported by a steel mast, and its center is L high above the ground. So we have here the dimensions. Okay, the height is over here. We have the b. Okay, we have the a, and we have the L. Okay, later we'll redraw this anyway. So just to show you the given information based on the statement. And we have to consider here the weights of the design and the mast, which are, well, we have here W, the sign, and we have also here the weight of the mast. Okay. All right, so we have here, and let's try to draw the feed body diagram of that give an example. Okay, where there will be no exact solution, because the given are in variables. So let's just try to see, okay, how the free body diagram should be constructed. So we have here the weight of the, okay, sorry, let's try to use the the annotation using this other software. Okay. Okay, so let's try to, that's too big. All right, so this one. Right, so we have a the force of the W, okay, of the wind. Okay, that's V. But we have to find out what that value is. Okay. The weight is given. It's going to be, let's try to put it this way. The weight is WS, and we have the dimensions of this as A, and the height is B, right? So we have also here the length L, which is the height of the mast. And we have here, so we have here acting on the, this is going to be A over 2. That is the point of action. Okay, the location of the point of action of the weight and the V. Now, we know that wind pressure is actually 0.00256 V squared. And we know that the wind is acting on the whole surface of the whole surface of the sign. Thus, we have the force. Okay, that's going to be the P times the area. So we have 0.00256 V squared times area is going to be AB. So it's AB. Okay. The force of the, let's try to put it wind. Okay, the force of the wind. So we have here FW. Now, because we have this is the whole body, right? So we will have a certain reaction over here that's going to be, okay, a reaction force and then a moment force, because this is going to tip over, right? So this is there's going to be a torsional reaction at the bottom. Again, this is just statics. We're not looking into the stresses yet, okay? All right, so let's try to do now or identify the stresses in the bottom. Okay, so we have from our given. Okay, let's remove now the, let's forgo this this what do I say, this design. Okay, so we have the force of the wind acting on the, all right, sorry, I have to move over here. Okay, all right, all right, so I'm back. Now the weight of the mast is going to act on its middle. Okay, we have here WM, and okay, since this is going to, there's going to be a moment about the because we have here the weight, right? So it's about this about the sign. So there's going to be a moment, okay, about this point, the center. Okay, ms equals, it's going to be ws, right? Ws times a2, okay, a over 2 pala. Oh, it's a over 2, okay. So we have here now, okay, ws itself acting on this portion, and we have a torque that is equal to T or TW, okay, that is TW, and we have it, the value of it as FW times A over 2, okay. So the force of the wind, okay, is going to create a torsional, okay, because it's going to be acting on this portion, so it's going to rotate the mast, okay. So this is torsional, so it's supposed to be like that, but let's put it that way. All right, so now on to the the bottom, okay, or the reaction at the bottom. So this would have a reaction again, as drawn a while ago, and then a torsional force, that's T. And then we have here a V. And then we also have here an M1. And another M2 is expected to be, okay, bending moment, okay. No, it's a moment, okay. That's going to be expected over there on the other side, okay. Again, this is going to be along this plane, okay. So those dimensions. Right, so that's the solution to this one. Let's proceed now to well, the biaxial loading that was introduced a while ago, and there are a lot of how do I say this? The different examples of biaxial loading that happens most in pressure vessels. This is what they or what is termed as thin-walled pressure vessels, and we have here in Figure 2 an example of such in an overhead water tank. There are a lot of examples: balloons, other pressurized vessels that are filled with fluids or gases. Okay, fluids is more generic again than gas, because fluid can be gas or liquid. So any thin-walled pressure vessel should have their radius, okay, the thickness, the ratio of such, okay, should be greater than or equal to 10. Okay, otherwise, this simplified analysis or solution is deemed inappropriate. All right, so what happens, okay, in this scenario in thin-walled pressure vessels is that, okay, let's try to analyze a cylindrical vessel. Okay, let's try to put it this way. Okay, so we have, let's try to rotate this one, rotate the rotate the overhead water tank to this direction. So we have something like this, right? So we have a tank that looks like this, right? And this is going to be the cross section. Now we're going to take a very small portion of it, okay, an infinitesimally small portion, dx, and so we have here a small, okay, portion, dx times a certain dimension, okay, and we have here that infinitesimally small portion encountering forces that would strain it, and the stress is termed as the longitudinal stress, okay, and we have here the circumferential stress or hoop stress, because it's occurring at the or along the plane of the along the circumference. Okay, so this one is longitudinal because it's along the longitudinal portion. Now let's try to cut this off and put that in here. Now, what happens is if you have if you cut it along this dimension, for example, remove the ends, or okay, the ends. We have here the force, okay, or the force is going to be what? It's going to be the force, okay, is going to be equal to the pressure times pi r squared, okay, and the edges, okay, the edges would have to react because it's going to fail, or it's expected to fail along that dimension or that location. So it's going to have an equally distributed reaction towards this force, right? And in this kind of or given diagram, okay, so we have this as, okay, this is going to be a stress times an area. So we have the longitudinal stress, as we have identified a while ago, times 2 pi r t. Okay, right? So P, okay, or we can now find for the longitudinal stress, and we can equate this one so that, okay, we have all right, it's going to be 2 pi. Okay, wait, sorry. Let me just check my solution. Okay. All right, so this is correct. This is correct, right? So we have another portion. Okay, so we have here the upper the cut, okay, along the longitudinal section. Okay, so we have the forces, the same force, right? So we have the same force, okay, happening over here. Okay, so we have the same force that is the same magnitude. So that's going to be F equals to P. So let's just let's put it correctly. Okay, so it's P times the quantity pi r squared, r raised to 2, and we have the reaction force along this portion of the and this is actually the in relation to your the circumferential stress or this hoop stress. Okay, so the hoop stress is, or the force is going to be equal to, all right, is going to be times, this is going to be an r, right? So you have an r over here, and you have a certain thickness of the tank. Okay, so we have here the 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 force, okay, of this magnitude. That's going to become C. That's going to be the circumferential stress times T times dx. Okay. Okay, so solving for C now, we get what? We get C equals F. So it's going to be 2 pi r dx. Sorry, let me just see if this is correct. So we have, okay, so the force is, okay, this is wrong. I think this should be, oh, sorry, there's something wrong with the let me just correct this one. This is incorrect. Okay, so we have to correct this one. That is actually 2, okay, P times 2 times r times dx, because we have the radius. So this is 2r supposedly, sorry. That's going to be 2r times dx, right? So that's going to be now okay, so this is going to become F, right? So 2, okay, 2c, the 2 times the circumferential stress. So that is going to be 2. This will become, sorry, incorrect again. All right, let's try to correct this one, and let's try to move the solution at the upper part or the lower part, EV, so that it has more space. All right, so we have here the force equal to P times 2r dx, and we have this as the force, okay, the reaction force. Let's just put it P. Oh, no, sorry. Let's not put it P. It's the same P. Okay. That's the pressure. So we have reaction 1. So F equals 2R. Okay. So we have here P times 2R dx times 2R equals to 2 times the circumferential stress times the thickness times dx. Dx cancels, 2 cancels. We have P times R equals the circumferential stress times the thickness left. So the circumferential stress is then, the circumferential stress is then PR over T. Right. So we have the circumferential stress known. We have to find the longitudinal stress, and that would be, okay, so this is the final equation for the circumferential stress. The longitudinal stress is, again, this is incorrect. I think this is correct. Let me see. Yeah, this is correct. So we have here the force and the reaction R2 equals the longitudinal stress times the quantity 2 pi r times the thickness. I think we have to include the dx here. Let's try to include the dx. Yeah, it's included because yeah, it's multiplied times that portion. No? We have to include the dx. So we have here d times dx, right? So to find for the longitudinal stress, okay, we get the longitudinal stress is equals, actually, it's actually C over 2. Okay, and it is PR over 2T. Right? Now, what happens if you have a spherical portion? Okay, a spherical, instead of it being cylindrical, so you have a cylindrical or a spherical vessel. So you have the same, actually, you have the same forces or actions on the edges or the cross section cut of the end of the vessel. We have the same force, right? So the F is going to become P times pi times R squared, okay? And then you have the sigma c, okay? The sigma, we just have one sigma, so it's going to be 2 pi r times the thickness. So we have this as PR over 2. Right? Try to solve for an example of this kind. Okay, let's try to do an example, and let's proceed with this given. We have a cylindrical still water tank with hemispherical end caps as shown, and the inner radius of this, okay, is, so the inner radius is from here to here. That is going to be 24 inches, and we have the thickness of the tank at 0.25 inches. Let's see if it's possible to solve this as a thin wall pressure vessel. So we have the radius over the T. So 24 inches over 0.25 inches. The inches cancels. We have a value of what would that be? It's 24 over 0.25 as 96. So this is a this is a thin wall pressure vessel. So let's try to solve this one. Let's solve using whiteboard. Sorry. Let's try to share another screen. So we have here, okay, the cylindrical vessel, and we can always go directly to the solution because we know that it's cylindrical. So we can solve using the first portion of the discussion where we used the equations, this one, right? PR over T, or the other equation, PR over 2T, or simply the circumferential over 2. But there's a catch, okay? So there's a spherical end caps of the vessel. So we still have to solve for the stress at this spherical portion. So it's going to be PR over 2T, okay? So let's try to solve it, right? We're trying to find the stresses. So it's going to be 125 pounds per inch, okay, times it's 125 psi, 24 inches, and you have the thickness at 0.25. Solving this, we get the value of inches. So we get 12,000 psi. Okay, that's the circumferential stress. And we have this 12,000 psi over 2, we get 6,000 psi. Next up, we get the stress at these vertical end gaps, which is, okay, 125 pounds per inch squared times 24 inches all over 2 times 0.25. That is in inches as well. So we get 6,000 psi. These are the final answers for this problem. And now, okay, we are able to solve for the stresses in the water tank. If they are going to fail, that depends on the properties of the material. Now, in the proceeding discussion, okay, we talk about the axial and lateral loads, right? And we have here the diagram where we have a beam that is supported at both ends, but differently. We have a pin type connection at one end and a roller type bearing in the other. Okay, so it's a rolling support. Now we have here two forces acting on it, three actually. We have force 1, force 2, and a force P. Now taking the cross section of this beam at MN, so we get the cross section over here. Okay, so we have the cross section over here, right? Now, what happens to this this beam when it's encountering axial and lateral loads? So, okay, we have here, for example, we take this portion, okay, of the beam, okay, to see what happens across MN. So we have, if it's going to be due to the force P, then we have a distributed load over here. The stress is distributed. Okay. It's going to be, stress is going to be P over A, right? Now, what happens to the portion? Because we have here a moment, okay, about y by the forces F1 and F2. So there's going to be bending. Now, if we consider it to be distributed equally, so we see it something like this. Okay. Distributed like that. Okay. So this is going to be to the moment, and this is going to be bending, which is solvable using this formula. Okay, and we denoted this as A and B because they're acting on the same beam, so we can add them, and this is the concept of superposition. Okay, so we add the stresses, so that what we get this portion is, okay, is something like this. Okay. Oh, sorry, it's going to be at this direction, because we assume that the stresses are acting in separate or the opposite direction of the bending moment. Okay, so we have this as the final stress resulting from both A and B. All right, and this is again the concept of superposition. Now, what if the load is not as shown? So we, what if the forces, right? The P over A, okay, is greater than, okay, the bending moment. We know that in this scenario, okay, the P over A is going against the bending moment. But they are of almost the same magnitude. Okay, so if this is true for, if this is true for P over A greater than M, okay, the absolute of M times C over I. What if oh, sorry, this is going to be below, okay, but if in the opposite case, we will have a different setup, since if P over A is greater than the absolute value of M times C over I, what we would get is something like this. Okay. Right. And then we have the full cross section. Sorry, this is going to be supposed to be opposite, okay? Opposite direction, because it's going to be in compression while on the below the neutral axis. Okay, we've talked about that. The neutral axis, below it is going to be in tension. Now we're going to consider the deformation of a body. Deformation. The formula becomes P over A minus the quantity M minus P times the deformation. this is multiplied to y and divided by I. If um, the pressure or the pressure or the resulting force is in compression, then still noting if this is true, then the whole cross section will be in compression as well. Okay, but graduated, similar to this one, just in the opposite direction. All right, so we are done with the combined axial and lateral loading. Let us look into what happens, okay, because we have to proceed to the transformation of stress, and this is very important in cases where there are failures inside a structure or a component. So let's look at the circumferential and longitudinal stresses that happens in a infinitesimally small portion of the pressure vessel that we were talking a while ago. But if we have we introduce a shear stress in this kind of diagram, let's see, for example, it's like this. Now, if we do have a shear stress over here, then we are now proceeding towards what the discussion is progressing into. It's the transformation of stresses. Okay, if a certain body, okay, is encountering a combined normal and shear stress, it may fail at a certain point because within the body where there is a significantly greater stress, okay, when these two force or loads or stresses are combined. And that is going to be a topic in the next lecture. I will see you by then, and thank you for listening.